So in 7.4, we want to find the value of some of our other trigonometric functions. So we want to find the values of sine alpha, cosine alpha, tangent alpha, cosecant alpha, secant alpha, and cotangent alpha for the point -1 over the square root of 2 and 1 over the square root of 2 on the unit circle. So to remind us, first of all, here's our definitions of the not sine and cosine, because we haven't used cosecant, secant, and cotangent as much. So if we look at our point, -1 over root 2 and 1 over root 2, what quadrant is that point going to be in? Well, x is negative and y is positive. So we're going to be in quadrant 2. So here's our unit circle. And in quadrant 2, we're going to have something that looks like this. And we know our point is -1 over the square root of 2. So this side is -1 over the square root of 2. That's our x. And our y is +1 over the square root of 2. So this point is actually on the unit circle. So then, since we're on the unit circle, we know the hypotenuse has to be 1. So our reference angle here is alpha, and our actual angle theta is here, but we can figure out what our angle is. So if we want sine, I wrote those backwards for this one, because alpha is what we were asked to find. So then that would be our reference angle. So our sine of alpha would be the value in this quadrant. Well, on the unit circle, sine is opposite over hypotenuse, or y. So we would get this. Cosine alpha would be x, which is 1 over the square root of 2. Tangent on the unit circle is y divided by x. So that's 1 over the square root of 2 divided by 1 over the square root of 2. And anything divided by itself is going to be 1. All right, so that's sine, cosine, and tangent. Now we have cosecant, secant, and cotangent. Well, cosecant of alpha is the same as 1 over sine alpha. So that's 1 over the square root of 2. Or if we multiply by the reciprocal of the denominator, we get the square root of 2. So it's worth noting that these are reciprocals. We're going to get the same thing with secant. Secant alpha is the reciprocal of cosine. Well, if cosine is 1 over root 2, its reciprocal of 1 over the square root of 2 is square root of 2. And lastly, we want cotangent alpha, which is going to be 1 over the tangent of alpha, so the reciprocal of tangent, and the reciprocal of 1 is 1. So that would be our value for all of these. With one exception, what did I do wrong in every single one of these? So this is important. What quadrant is this in? Well, x is negative. I'm in quadrant 2. So in quadrant 2, which coordinate is negative? X. So that means this one's negative. That means this one's negative. So this is -1. So the sign is fine. This one's negative, and this one's negative. So we have to be careful. In quadrant 1, every trigonometric function is positive. In quadrant 2, since x is negative, cosine is negative. In quadrant 3, both x and y are negative. So then, if both x and y are negative, sine is negative, cosine is negative. But if they're both negative, a negative divided by a negative is a positive. So tangent's positive in quadrant 3. And in quadrant 4, x is positive and y is negative. So sine's negative, cosine's positive, and tangent would be negative. So we have to take care and calculate the sign appropriately. All right, the next one is for you guys. And we want to use negative 2 pi over 3 to find the values of sine, cosine, tangent, cosecant, secant, and cotangent. So before I turn you loose, I'm going to give you a hint. Hint, negative 2 pi over 3 is coterminal with 2 pi plus negative 2 pi over 3, which is 4 pi over 3. So our coterminal angle is 4 pi over 3, and 4 pi over 3 is in quadrant 3. So if we draw a triangle down in quadrant 3, so we know for our reference triangle that one side has to be along the x-axis. So it's going to look something like this. Our reference angle is then going to be pi over 3. So then we know that we're going to be using our pi over 3, pi over 6, 90 right triangle, so that's a 1, 2, square root of 3. But in quadrant 3, we have both x and y are negative. So that would mean that's negative and this is negative, right? Because our x-coordinate would be this side and our y-coordinate would be this side. So now we can use this triangle to find our values. So we would have the sine of negative 2 pi over 3. Well, sine is opposite over hypotenuse, so we're going to get negative root 3 over 2. Cosine of negative 2 pi over 3 is adjacent over hypotenuse, so that's negative 1 over 2. Tangent of negative 2 pi over 3 is opposite over adjacent, so we're going to have negative root 3 over negative 1, so a negative divided by a negative is positive, so we get the square root of 3. The next 3 we can get from this, using the fact that they're reciprocals. So the cosecant of negative 2 pi over 3 is 1 over the sine of negative 2 pi over 3, which is just the reciprocal of what we got here. So it's negative 2 over the square root of 3. The secant of negative 2 pi over 3 is the reciprocal of cosine. So we flip over cosine and we get negative 2. And lastly, the cotangent is the reciprocal of tangent. And the reciprocal of tangent is going to be 1 over the square root of 3. So that would be the values of our 6 trigonometric functions at negative 2 pi divided by 3. So now we want to talk about even and odd functions. So our definition for an even and odd function is as follows. So a function is even if f of negative x is equal to f of x for all x in the domain of f. Graphically, an even function is symmetric with respect to the y-axis. A function is odd if f of negative x is equal to the negative of f of x for all x in the domain of f. Graphically, an odd function has rotational symmetry with respect to the origin. The rotation is pi radians, or 180 degrees. So, just to show you a couple of graphical examples, if we were to graph y equals x squared, this is the simplest example of an even function. If I fold it over the y-axis, the two halves of the graph would land on top of each other. That's y-axis symmetry, or a reflective symmetry in this case. If we go to x cubed, this is an odd function. And we say it has rotational symmetry of 180 degrees about the origin. If you take that, your calculator, after graphing y cubed, and you turn it upside down, rotate it 180 degrees, the graph looks the same whether it's upside down or right side up. That's our rotational symmetry about the origin. All right, so it turns out that algebraically thinking about even and odd functions, we'll notice that even functions eat minus signs, and odd functions, the minus sign moves out in front. So basically, this is saying if a function is even, it has the same output at x and negative x. A function is odd if its outputs are opposites at x and negative x. Well, let's see if we can figure out what's going on with sine. So if we take sine theta, it's going to equal something. So let's draw a reference angle. So if this is my reference angle theta, negative theta would be the exact same angle, but it would be in the opposite direction, right? Because it's a negative angle. So then if I look at my chart here, we know that sine theta is equal to y. So this is at some point xy. But if I do the same thing, but I go in the opposite direction, the x would stay the same, but my y would be negative. So then this would tell me that the sine of negative theta equals negative y. So then combining these two things, so solving for y is equal to the negative sine of negative theta. So that would give me that the sine of theta is equal to the negative of sine of negative theta, or sine negative theta is equal to the negative sine theta. Chaining all those together. So then by definition, this tells us that sine is odd. We could do something similar with cosine. Cosine is x. So if I go cosine theta, I get x. And if I do cosine of negative theta, I also get x. So then combining these two, I get that the cosine of negative theta is equal to the cosine of theta. So cosine is an even function. And we can keep going. So then secant and cosecant are going to be the same as sine and cosine. The only one we really have left to think about is tangent. But tangent theta is sine theta over cosine theta, which is an odd divided by an even. And an odd function divided by an even function will also be odd. So basically, we have the following rules when combining even and odd functions. For either multiplication or division, if you have an odd times an odd, or an odd divided by an odd, you'll get an even. If you have an odd times an even, you'll get an odd. And if you have an even times an even, you get an even. So this may or may not help you remember it. Odds behave like -1, and evens behave like +1. So if you have a -1 times a -1, it equals a +1. A -1 times a +1 equals a -1, and a 1 times a 1 gives you a 1. So if you think of it that way, it will help you remember the patterns, whether or not you are multiplying or dividing. So two negatives make a positive, so the product or quotient of two odd functions is even. A positive and a negative gives you a negative, so a product of an odd function and an even function will be an odd function. And a positive times a positive is positive, so an even times an even will also be even. So then that's how we got tangent being an odd function, is an odd divided by an even would give us an odd function. All right. So using all of these, with our reciprocal identities, as mentioned, will tell us the evenness and oddness of each. Now that's not the path that we're going to take right now. We wrote these down earlier, but we do want to mention them explicitly again. So the sine is equal to 1 over the cosecant of theta, or cosecant of theta is 1 over sine. So these two trigonometric functions are reciprocals of each other. We have a similar relationship for cosine and secant. So they are reciprocals of each other. And then tangent has the same relationship with cotangent. So these are our reciprocal identities. And when we say an identity, we mean an equation that is always true. So one of the things we will need to do often in trigonometry is replace things with what they are equivalent to to either solve or simplify expressions. So if you ever have a cosecant, you can always replace it with a 1 over sine. So whenever we need these, we will always have them. So it's worth noting, these are on that first handout with the reference triangles, these definitions for the reciprocal identities. So let's go ahead and do a couple of examples. So we wish to simplify the following expression. Secant t divided by tangent t. So first thing we want to note is that secant t is equal to 1 over the cosine of t. We also have, by definition, that the tangent of t, or this is by a theorem actually, is the sine of t over the cosine of t. So putting each of these into our expression, we have 1 over the cosine of t divided by sine t over cosine t. And if I have a fraction divided by a fraction, it's the same as multiplying by the reciprocal of the denominator. So 1 over cosine t times cosine t divided by sine t. Now we have a cosine in the top and a cosine in the bottom. So they reduce out, and we get 1 over sine t. And we can rewrite 1 over sine t is the same as the cosecant of t. And that's our reciprocal identity. All right. Let's take a look at our next one. So we have this time cotangent and cosecant. So cotangent is going to be the same as 1 over tangent but tangent is 1 over sine over cosine. So making it a fraction over 1, that's 1 over 1 times cosine x over sine x. So we're just going to get cotangent is the same as cosine x over sine x. Doing something similar with cosecant. Cosecant is 1 over sine. So then we put these together, and that gives us cosine x over sine x times cosecant x, which is 1 over sine x, and we end up with cosine x all over sine squared x. All right, let's keep going. So some trigonometric identities are, so since trigonometric identities are equations, we can use the properties of equations on both sides, which means we can find alternate forms of almost every trigonometric identity. So for example, if we start with the Pythagorean identity, which is sine squared plus cosine squared equals 1, we can derive a few different equivalent identities which are in this box. So we have sine squared x plus cosine squared x equals 1. If I divide both sides by sine squared, well, anything divided by itself is 1. Cosine over sine is tangent, or is cotangent. And 1 over sine is cosecant. Oh, well, this is another identity. And I've got these backwards. In the table. Because when we divide by sine, yeah, we get cosecant. And this one is cosine. So in that table, I have those bottom two things reversed. But in essence, the key thing here is since they are equations, we can use the properties of equations on both sides. So we can add things, we can subtract things, we can divide by things, and we can multiply by things if it's a known identity. And this creates more identities. So this is why we call this the first Pythagorean identity. All of these are the rest of the Pythagorean identities because they're really just the first one when we've done something to it. So the big idea is when we need trigonometric identities, they're not always going to be set up in the perfect form for us to use. We may have to massage the algebra a little bit to get it into a form that will be helpful. All right. More definitions, I know. Our next one is that of a periodic function. So a function is periodic if there exists numbers p such that f of x plus p is equal to f of x for all x in the domain of f of x. The smallest value of p is called the period of the function. So now we want to ask ourselves the question, well, what is the period of each of the trigonometric functions? Well, if we go back to our idea of the unit circle, it'll help us visualize what's going on. So sine is the y-coordinate, so it's positive, positive, negative, negative. So it would look something like this. It starts at 0, goes positive, comes back to 0, and then goes negative down to negative 1 and comes back to 0. So sine's got to look something like this. But after we've completed one trip around the circle, what's going to happen? Well, if I go around once, all of my coterminal angles are going to give me the same values. So the period for sine period of sine is 2 pi. Similarly, if we start with cosine, cosine is the x. Starts at positive 1, the x value goes to 0, and then goes to negative 1. So it starts at 1, goes down to 0, and then goes to negative 1, and then goes from negative 1 back to 0, back to positive 1. And then I'm back to where I started. So this is going to be what my cosine function looks like. So the period of cosine is 2 pi. Okay. So we have our sine, we have our cosine, we have their periods. So then tangent is y divided by x. Well, we're dividing by x, so that tells us that x can't be 0. Well, x is the cosine function, right? So where does the cosine function equal to 0? Well, the x coordinates are equal to 0 here and here. So it looks like its period would be from here to here, halfway around the circle. So its period halfway around the circle is going to be pi. So the period of tangent because we're not allowed to divide by 0. So once we do so, it's going to flip it over into a new copy of itself. The reciprocal functions all have the same periods, but their domains will be slightly different. All right, so we want to use a calculator to find the cosecant of pi over 8. So if you grab your calculator, you'll notice something. There is no cosecant button. On our calculator, we have sine, we have cosine, and we have tangent. So we must use the reciprocal identities. So the cosecant of pi over 8 is the same as 1 over the sine of pi over 8. So we grab our calculator, and we're going to go 1 over and the sine of pi divided by 8. And we will get this value. One thing we need to double check, if you didn't get this value, make sure your calculator is in radians and not degrees. So if you got something else, it's most likely your calculator is in the wrong mode. So the reciprocal identity for cosecant is 1 over sine. And our calculator does have a sine button. So to calculate the cosecant of pi over 8, we would calculate 1 divided by the sine of pi over 8. All right. Last one's for you guys. Find the cotangent of 5 pi over 8. All right, so let's go ahead and finish this. So the reciprocal identity for cotangent is 1 over tangent. So the cotangent of 5 pi divided by 8 is 1 over the tangent of 5 pi over 8. And then that is calculator food. So we go 1 over the tangent of 5 pi, and we divide that by 8. And we get the following value. So if we need to calculate any of the reciprocals, so secant, cosecant, or cotangent, we have to write them as 1 over using the reciprocal identities and calculate that, because there is not a cosecant, a cotangent, or a secant button on your calculator. All right, that is